Okay, I think that was the sound of recording has begun. All right, good evening, everybody. In our webinar series this evening, we're going to have a discussion or a presentation on net zero construction. And yeah, we'll get right into that presentation now. I have about 25 slides if people want to track my progress through this. It's a topic I'm fairly passionate about. Sometimes I'll wander off topic. I'm going to rely on my co-pilot here to keep me on point and moving forward. Having said that, if you have questions, please go ahead and raise them as they come up. I know sometimes if I have questions during a presentation, by the time we get to the end, I've forgotten them. So the group's not large. I'm happy to answer people's questions to the best of my ability when they arise. So we're going to talk about net zero construction, how you do it, and why you would be thinking it's something you would like to do. And this is primarily from the primary focus for the presentation is on investment properties. Having said that, much of what we cover applies to any building that you're going to do for residential purposes. So talk a little bit about our agenda here. So we're going to talk about what is a net zero home or building. We're going to talk about energy use in a net zero home, how to achieve net zero from a construction perspective, some of the risks associated with net zero construction, what are its costs and benefits, how is it relevant for developers, and how would you build to net zero? So we'll cover those topics, and I guess not a bad idea to say I did the net zero builder training last year, and before you were able to take the net zero builder training, even though I have an engineering degree, they still required me to do a preliminary course on advanced building science. In total, it was about 5 days of training, and about I think 700 slides in the training material. So as you can probably imagine, with 25 slides to cover it, I'm not going to go into anywhere near the depth that was done in the training, and that wasn't the purpose of this evening. This is to give a context on what net zero is, how it's approached from a construction perspective, and why it's beneficial to, at least why I think it's beneficial to do it for even development projects. So with that precursor, so what's a net zero home? A net zero home, I'm just going to read this off the slide, is a home that is recognized by Canadian Home Builders Association on the basis of attestations, which is to say sworn reports, by the builder renovator, its qualified net zero service organization, and a qualified net zero energy advisor to have met the technical requirements, including the energy performance rating using NRCan's EnerGuide rating system, to be designed, modeled, and constructed to produce as much energy from on-site renewable energy sources as it consumes on an annual basis. That's a pretty big mouthful. It's a home that's sufficiently energy efficient that you can, primarily using a solar array, generate as much energy with that solar array over the course of a year as your home is expected to consume in that same time period. The graph on the right is taken straight from the National Research Council, and it shows for context and NBC 9.36 is a 2015. That's a building that meets or is compliant to the 2015 building code. And then we can see the series of steps that show how much more energy efficient different buildings are. So we have not the latest, but the 2005 version of an R2000 home, which improves by 10% on that. We have an Energy Star rated home. Those were popular with builders. I remember seeing them 4 or 5 years ago. Maybe they're not popular anymore, but they give you a 20% reduction in your energy consumption from your home. Then we have the newer version of R2000, the 2012 version. That's a 45% in reduction in energy efficiency. And then a net zero energy ready home, they're anticipating a 70% reduction as compared to the National Building Code. So it's pretty significant work done to reduce the energy consumption in a building to achieve a net zero energy ready status.
So what is net zero energy ready?
So if you're a net zero ready, it means that you've been assessed by an energy modeler or an energy advisor that you've constructed a home that's energy requirements are sufficiently low enough that a future solar array installed in the future on your home would be large enough to provide the energy to get to net zero. So you've done the building good enough, you just haven't installed a solar array yet. So you haven't got the renewable energy source there. So that's net zero ready. Some few other notes. By 2030, Canada expects all new construction to be net zero. So this is not something that's far away in the future. The expectation
6 years only.
only 6 years. For those who are on the developing side or the investor side, to get access to CMHC's MLI Select program, one of the ways to do that is to achieve a 40% energy efficiency. And to get to that 40% energy efficiency, near net zero construction is needed even today. So the same things that would get you that energy. Oh, Dave's got a hand up. Go ahead.
Yeah, a quick question. So you mentioned here by 2030, all new construction to be net zero. On whose mandate? Where is the impetus for this coming from? Is it building code or is it something else?
No, it will be building code. That's the only way the government can mandate improve building standards is by making changes to the building code. So we have a new code coming in January of this year, and I think they're working on a rewrite that's supposed to implement the net zero requirements into the building code.
Okay, thank you.
And the target for that is 2030. Whether they get there, that's a whole different discussion. But when we did our training last year, this is what we were told. There, at least last year, the training was free. Anybody who has a construction company and wanted to be trained as a net zero builder or net zero renovator, you could attend the training at no charge. And it's one of the reasons for that is the government sees one of the significant bottlenecks in terms of mandating this construction standard is that there's not going to be enough trained builders to be able to do it. So they're working now to set up an environment where when these requirements come in, there's enough trained people to do the work.
Okay, thank you.
You bet. And the last bullet on this one is by 2050, there's an expectation that all existing buildings will also have been renovated and retrofitted to achieve net zero. So with this, knowing this is coming down the road, you'd be remiss at this point to do new construction and not factor it into your plans. Okay. So a little bit of background. Typical 1982 home, you have 75% of your energy cost goes to heating, 15% went to hot water, 10% went to lights and appliances. So I think air conditioning was not standard in 1982. Your heat was your primary energy consumer. Hot water was also a decent sized energy consumer. It's interesting to note, I've got a couple of other pie charts like this, and hot water almost doesn't change over the time period. So now we look at what a 2024 code compliant home would look like. And you can see water heating now slightly larger, but I think it's because the overall energy requirements have gone down for a 2024 home. So of note now, air conditioning is now standard. Heating is still our largest energy consumer. Lights and appliances have increased to be the second largest energy consumer. I think that's a combination of the overall energy requirements for heating and cooling and water heating having dropped a little because the equipment's quite a bit more efficient. And the occupant load's going up. I don't think we had 10, 12 computers in every home back in the 1980s like we do now. One TV, although it consumes a lot more energy than the TVs we have now, but still only one TV and probably not quite as many appliances. So occupant load's definitely the one that's gone up. Hot water is still a significant energy consumer. And now let's take a look at what a net zero home would look like from 2030. And now we can see that occupant load is actually the biggest single load in your building. So let's talk through that. Environmental energy consumption is now only less than a third of your total energy consumption. It used to be 75% in the 1982 home. So we see a big reduction there. Hot water is now our third largest energy consumer, and it's back at that 15% mark. Occupant load has grown from 10% in 1982 to over 52% in a net zero home. And of course, as your other energy requirements drop, and your user load stays the same, or maybe in some cases goes up a little bit, as a percentage of the total energy, it becomes the predominant load. So that's what the energy requirements for a net zero home would look like as compared to a non-net zero home, or compared to an older home like a bungalow, or even a two-story home built in the 80s or prior to, that hasn't been improved. So pretty big difference. It just occurs to me that it would have been helpful, and I haven't done it, so I can't show what the total energy consumption for each of those buildings would have been, and I have that chart somewhere, so my apologies for not putting it in here. But the total energy, well, actually, I guess we can briefly take a look here, where this is a 2015 home, and a net zero home is in the 26 to 32 gigajoules range, which is only 30% of what that's standard 2024 code compliant home would have been. So pretty big difference. Scroll down again. Okay, so let's talk about how we achieve net zero. So we achieve net zero through improving your thermal enclosure, through efficient heating and cooling, through advanced water heating systems, efficient lights and appliances, optimal site planning, and providing some renewable energy source. So these are the aspect. We'll go through each of these in varying levels of detail, depending on how broad a contributor it is to achieving excuse me, to achieving net zero. But these are the things that you have to factor into your design and your build of a new building if you're gonna be shooting for a net zero certification for it. So what does an improved thermal enclosure look like? Well, we need to reduce heat transfer. And there's three primary types of heat transfer. We have conduction, this guy right up here. It's heat passing through a solid. We also have convection, which is air leakage through holes. We used to call that natural ventilation. We don't like to have that concept anymore. You can see cold air coming in here, warm air going out the top of your building. And we'll talk a little bit more about that bottom and top in a few slides. Then we have radiation, which is warm surfaces radiating energy to cold surfaces. So in the daytime, in the summer, you've got the sun heating your roof, which lets heat come in. You've also got energy coming in through your windows, some of which is rejected, but some of which gets through. In the nighttime or in the winter, we have that same, your body gives off, radiates to the cold surface, which would be the glass primarily in this case. And then we have during heating season, of course, heat transfers to the environment from the home. So that's right here. We see the heat going out. Here heat's going out, and here heat's going out. And during the cooling season, we have heat transfer from the environment into the home. That's this side of this line here, which is heat coming in. Here it would be cool coming in and heat going out if you're in the daytime. So let's talk about how we can fix that. Actually, I'm going to just go back here. Stand by for a second, folks. There. Okay. So let's talk about heat loss. So where do we typically lose heat through a net zero ready home? So this is a well-designed and well-built home. Of our energy loss, we're talking about 27%, a little over a quarter of our energy losses through our windows and doors, 25% out through our walls, 25% through our foundation, and then the remaining through air leakage and through the ceiling.
This is from regular construction.
Nope, this is for a net zero ready home. So if you've done a good job of building it, like it's the total energy loss. So you're still at 100%. This is how it would split up. If you haven't done a really good job of doing your home, this air leakage is going to be quite a bit larger percentage. Okay. Conduction goes through windows, walls, floors, and ceilings. So windows, walls, floors, and ceilings. Air leakage through holes, gaps, cracks, plus ventilation, which is planned air exchanges. So primarily up there, air leakage. Radiation, heating, and cooling through windows and the roof in the attic, if you remember the slide from before. So we'll talk a little bit more about conduction losses now. So conduction losses, how do we eliminate them or reduce them? You can't eliminate them, it doesn't stop, but you can reduce them down to the point that they result in a very small amount of energy loss that way. So one common way, actually, I think pretty much mandated way, is to provide continuous insulation, which eliminates thermal bridging. And if you think about how a house is built today, normally, you have a wood framed wall with an OSB or some sheathing on the outside, and you're going to put batt insulation in the cavities between the studs, and then you're going to close that wall up, and that's your standard wall. So continuous insulation goes on the outside. It can go either between the cladding and the studs or on the outside of the OSB sheathing, and it's a continuous layer of some type of insulation. It could be expanded polystyrene. It can be batt insulation that's been fixed to the outside of the building, but it provides continuous insulation. There's no thermal bridging, so there's no penetrations of low R value materials in that layer, I guess, outside the sheathing, and that's a pretty powerful start to reducing your energy loss through conduction. Next one is triple glazed windows. And again, the R value of a conventional double glazed windows around R2-ish, and a well-built triple glazed window, the R value is about 5. Still not nearly as good as a wall, but 2.5 times better than a regular double glazed window. So it's a big deal. And in modern homes, the window area is significantly larger than it was in a home built, say, pre-1980. So the fact that the glazed area is increasing puts a premium on putting in good windows. You can increase attic insulation, although R50, R60 is pretty good. So we really wouldn't need to go beyond that. And that's pretty standard in homes now. So as long as you're getting to R50, not much of a need to increase it. And your energy loss is 1 over your R value. So 1 over 50 is 2%, 1 over 60 is like 1 point. The return after you get past R50 is very low, but you don't want to be less, excuse me, you don't want to be less than R50. And then increasing foundation insulation is that one's a pretty big deal too. You saw, if you recall the slide, think about 26% of your energy losses through your foundation. And for particularly homes in Canada where we almost all have basements, doing a proper job of building that basement, so putting insulation under the slab, putting insulation on the outside of your concrete walls, make a big difference there. Let's talk now about convective heat loss. So, convective heat loss. So it's basically air leakage. And what causes air leakage in your building? Well, first of all, you need holes. But even with holes, if you don't have a pressure differential between the inside and the outside of the building, you're not going to get a lot of leakage. However, there's a lot of things that we encounter in our environment that do encourage that leakage. First one's called wind effect. So anytime you have wind hitting a building, you have a high pressure zone where on the side the wind hits, and a low pressure side on the downwind side of that same building, and that increase in pressure on one side and decrease on the other creates a pressure differential across your house, and it encourages air to leak through all the holes it can find. Stack effect is another concept. It has to do with cold air coming in near the bottom and the bottom of your house being generally colder than the top. So hot air rises, and that hot air rising was going to find a way to leak out through any gaps it can find in the top, and you're going to bring in cold air at the bottom. And then the combustion ventilation stack effect just described. Mechanical or ventilation effect. If you have a gas burning appliance in your building, it's going to vent to the outside. It's combustion gases, and that's going to create a low pressure, which is going to encourage air to come in. If you're running the exhaust hood, either the one in the bathroom or the one over your stove, or even if you're running your dryer, all those things create negative pressure, and it's going to pull air into your building. And the only solution to reducing convective losses is to improve your air barrier. And as an added bonus, if you improve air barriers, you also tend to reduce moisture movement, which is a desirable thing to have in building science. So the less air that moves from warm to cold or cold to warm, the less moisture you're pulling out or bringing into your environment, and that's a good thing as well. Let's talk a little bit about, so MERB is multi-unit residential building. So multi-unit residential specific convection. So if you're talking about a single family home, your air barrier is between the inside of your home and the exterior of your home. If you're talking about a multi-unit residential building, when you talk about the air barrier, you're talking about compartmentalizing a suite in its entirety. So you're sealing all the exterior walls, ceiling, and floor penetrations. You're also sealing all the common wall, ceiling, and floor penetrations, and ceiling penetrations to all common spaces. So those two are almost the same, might even be the same. This is to get the same certification, because there is a certification for multi-unit buildings. It's different than a single family home. That the standard's a little different. It's not quite as high as it would be for a single family home to achieve a net zero as a MERB. But you do have to, when they come to test, so you do a blower door test as part of your certification when you're doing a certification for a single family home. And when you're doing a certification for a multi-unit residential building, they do blower door tests on all the different units individually. So that's why it's important to seal not just the exterior wall, but all the adjoining walls as well. And as an added bonus for a multi-unit building, when you do a good job of sealing it, you're also reducing noise and odor transfer, which is going to make your building a better place to live for your tenants. So the last means of heat transfer is radiation loss, and it's more significant during cooling season than it is during the heating season. That primarily because the amount of heat gain, solar heat gain you get in your building is how you size your air conditioning system. So the better job you do of reducing solar heat gain, the smaller your air conditioning system can be, and that affects the energy consumption that you get, which means the smaller your energy, the smaller your mechanical systems, the smaller your solar array needs to be to achieve net zero. So it primarily sunlight through exposed windows. And being close to cold, hot surfaces, being close to cold, hot surfaces causes radiant heating and cooling. The sunlight directly on the window is going to come straight in there. If you put an overhang or trees to block direct sunlight in through the windows, you're going to reduce the amount of energy that comes in. And if you're standing next to that window, I know when I'm near our windows here in our own home, and the sun's directly on me, you can feel the heat coming off the window. That's radiation. This is on the cold side. It's cold outside. If you get cold to a poorly built window, again, you can feel your body feels cold because you're giving off heat to that outside environment. So I already alluded to shading windows from direct sunlight as a way of reducing heat transfer, and coatings on windows that reject non-visible light's another pretty effective way. If you look at the stickers that come on windows, and all windows come with stickers, all windows in a net zero home need to come with stickers. And there's a solar heat gain coefficient, SHGC. And that's a number between 0 and 1, although you can't get to 0 because 0 means no light comes in. 1 means you're not filtering out any light at all. So a good solar heat gain coefficient would be, I've seen windows at 0.25, 0.32, and that means that the majority of the radiant energy that hits that window is going to be reflected by the coating that's on the window. So you get less direct heat coming in. The last thing is improve your attic ventilation and use lighter colored shingles. Again, if you see the top image here, heating on the roof makes it hot. And if you've ever been in an attic in the summer, you know exactly that it can be very, very hot up there. You can't work during the day when the sun's directly on your roof. Those heated surfaces radiate, and some of that radiant energy comes into your building. You want to reduce that. You improve the ventilation in your attic so that air moves better and it doesn't get as hot. And you put a lighter color shingle on your roof, and again, it doesn't absorb as much heat energy. It rejects more. So those are the means you can use to not take in heat through radiation. And if I remember correctly, I think I had to specify the shingles that we were going to use to our energy modeler so he could put that into his model properly. So you've done all these things. You've improved your insulation in your building. You've reduced your air leakage. You've reduced your radiant heat loading, and you've built this really fantastic envelope that does all these things. It comes with some unintended consequences. So comfort risks, primarily comfort risk is an air quality thing. You've now built an incredibly tight building that you don't get that same leakage of air in and out that you got in a 1982 building. So the need for constant supply of fresh air is absolutely there, and you're not going to get it through this envelope. It's built way too good for that. You also have wetting risks, and if you're not careful how you build that wall that I described, where you put the insulation on the outside, some of those insulations, particularly the styrofoam ones, they're non-permeable. So you put a continuous layer of styrofoam outside your envelope, your building sheathing, and you're now not letting moisture pass through that layer. So any moisture that gets into the cavity where the insulation is has no way out. If you've put a vapor barrier on the inside of the building and you've got a vapor barrier on the outside, one would say that you're not supposed to get vapor flow through it, and that's correct. The tricky part is any leaks, any air movement that you get through even pinholes, that air is going to come in with moisture in it. And once that moisture is in, if it doesn't have a way out, it stays in the cavity. When things get cold, depending on how thick your continuous insulation is and where your dew point occurs in your wall assembly, you can get condensation in that cavity. And there's actually been quite a few cases of not properly trained people trying to build a net zero home and ending up with wood rot and mold in those cavities because moisture gets in and can't get out. And that goes to indoor air quality risks. A combination of, you can get a wet environment that can create mold, and you're not getting the air changes you need to have good quality fresh air inside. Sick building syndrome. As we got better and better at making our buildings tighter and tighter, we started to notice a decrease in the healthy environment that was inside the buildings, and that was primarily because of the things I've made reference to, right? No air changes, moisture being trapped where you don't want it, and creating poor air quality. So now we get to ventilation of net zero buildings, and it's a necessity. It's a code requirement, but you absolutely have to. The better you make your building envelope, the more important it is to have good ventilation designed in and installed in your building. So we'll talk a little bit about that now. So mechanical ventilation, and that's basically having a system in your building specifically designed to exchange fresh air from the outside with stale air from your building. You want that ventilation to be balanced. You don't want your building. So we go back to the three images I showed you before for air changing, for convective heat loss, and you had stack effect, which is air going out the top and coming in the bottom, and you had pressure from one side to the other. You don't want to create your own stack or pressure gradient across your walls, so you want your ventilation to be balanced. You want to try to keep the building as close to neutral pressure as you can, because you don't want to encourage leakage other than through your mechanical ventilation system. So we do mechanical ventilation with a heat recovery ventilator or with an energy recovery ventilator. So there it is. So this is an image of what a heat recovery ventilator looks like. It's a box installed usually in your basement or some mechanical space, and you take in air from high humidity areas in your home. So you're usually pulling air from bathrooms and kitchens, and that air comes through a box, through a heat exchanger, and gets rejected to the outside. At the same time, you're bringing in fresh air from the outdoors. You're passing it through that same heat exchanger that the leaving air went through. So in a heating season, you're going to take heat from the air that gets exhausted, and you're going to use it to heat up the incoming air. In a cooling season, the reverse happens. You're going to cool down the incoming air by using the cool air that leaves. And then you're going to bring that fresh air in, and you're going to supply it into your living spaces, into your bedrooms, into your living rooms of your building. And you're going to do that pretty much constantly at a fairly low rate. There's calculations for what how many air changes you should have per hour in a building, and then these fans that you see here, they're usually pretty small. They don't move a lot of air. It's low energy and quite efficient, and it's making enough air changes so that your indoor air quality is very high, but it's in a controlled environment. So energy recovery ventilator. It's similar to an HRV. It's the same box. It's the same ductwork. The difference is in the heat exchanger core. In a heat recovery ventilator, moisture gets passed out and dry air comes in. In an energy recovery ventilator, there's some return of moisture to the inside. If you're in a heating environment, if you're in a cooling environment, you're going to reject the moisture to the outside. And as I say, it's a low power consumption unit because the fans are small and the flow rates are quite low, and they're high efficiency. So I think the units that we spec for our latest project are they're ERVs, and I think they're 77% efficient. So they pull a lot of heat. Either they pull it out or they return it, depending on whether you're in heating or cooling mode, passively, so you don't have to use your heating system to make up that heat loss. All right. So improved thermal comfort, efficient heating and cooling. Let's talk about that. So we talked about the building envelope. Now we're going to talk about efficient heating and cooling. And for improved thermal comfort, the things that we're looking to control to make a positive environment inside our building. Air temperature is the obvious one. Everybody's aware of that one. But there's several others that make a difference to how comfortable you feel in an environment. Your surrounding surface temperatures, and that goes to radiant heating. So if your glass is cold and you stand close to it, you're going to feel cold. If your floors are cold and you're walking around with bare feet on, or even without bare feet sometimes, again, you're going to feel cold. If you don't have good R values and your wall temperatures are low, you'll notice that. So you want your surrounding surface temperatures to all be in a range that your body finds comfortable from a radiant perspective. Humidity matters. Too humid is uncomfortable. Too dry, you're going to have skin problems. It's not going to be a good environment to live in, and your hardwood floors are going to dry up and crack up as well. So you want to keep your humidity comfortable. Air movement, drafts. If you have leaky windows, if you have leaks coming from behind your electrical boxes, that's going to be a problem for you. And then occupant activity and sensitivity. So depending on what you're doing inside the building and how you're clothed will determine how comfortable you are. Even if the environment stays the same, you can find it comfortable or uncomfortable depending on what you're doing and how you're dressed. So how do we account for all of these different factors that contribute to improve thermal comfort? So the first thing we do is we design for the occupant, not to the building code. We don't build to code. So there's building code requirements for how much heating and cooling you put in a building. And then there's allowing for ensuring that you make your occupants comfortable. There is no building code requirements for the surface temperatures. It's purely for heating and cooling. So you can do other things beyond what's in the building code to make sure your occupants are comfortable. Do proper load calculations. This is really important. You don't want to use eyeball or thumb or rough estimates of how much heat you need in a given room. There's proper load calculations that can be done by engineers, and you want to pay attention to the outputs of those calculations when you're sizing the equipment that you're going to put in your building. You want to optimize your heating and cooling equipment, and that's a follow-on from proper load calculations. Once you know how much heating and cooling you need in your building, make sure you're sizing your equipment to provide that. And bigger is not better. If your calculation says that a room needs 4,000 BTUs of heating, and you say to yourself, well, the smallest heater I can get that goes in there, let's say you're going to put a heat pump heater in there, and you can get them from as small as 7,000 up to 15,000. You say, well, I'm going to put a 15,000 BTU unit in there. You're not servicing yourself with that. You want to put the equipment in there that's sized properly for the room. If you have an oversized equipment, your temperature changes can be pretty quick, and you'll notice that, and it'll be an uncomfortable environment. Design better distribution systems. In the same way that you want to do proper load calculations for your heating and cooling, and you want to size your equipment properly, if you're using a distribution system like a ductwork system, make sure it's sized properly to provide the right amount of heat or cooling at the appropriate velocities, and make sure they're being put in the room in an environment that's not going to create artificial drafts or make it uncomfortable for your occupants. And then the last solution here is test and optimize your performance. And that's balancing if it's a distribution system. It's commissioning and testing to make sure that your heating system and your cooling system work as they were designed by the designer and intended by the contractor when they installed it. So what kind of systems are you going to use in a net zero building? And I say heat pumps as the primary heating and cooling equipment. So to get energy out of a gas system, even natural gas, or out of a conventional electric system, it's 1 watt or 1 BTU in gives you approximately 1 watt or approximately 1 BTU out. There's an efficiency factor that's there, but electric systems are really efficient, and current gas systems are also very efficient at pulling the energy out of the source. Where heat pumps differ from more conventional systems is you can get a coefficient on a heat pump like 3 to 1. So for every watt of energy that goes into the heat pump, it's just electric compressor, you can get 3 watts of heat energy out of it. And I think some you can get more than 3, but 3 is a good factor. And just explaining that coefficient of performance by itself is makes it pretty obvious why you want to look to heat pumps as your primary source of heating and cooling equipment. So if you need, let's say you need 50,000 BTUs in your building, that's actually a pretty big building. Well, at a net zero building, let's say you need 25,000 BTUs. So to get 25,000 BTUs from a gas furnace, you need 25,000 BTUs of input. From a heat pump that's operating at about a coefficient of performance of 3, you need about 8,000 BTUs of energy, and we'll get you that 25,000 BTUs out. So heat pumps are a pretty powerful means of providing that efficient heating and cooling. Improved building envelopes allow for smaller heating and cooling equipment. So where you might have needed a 60,000 BTU furnace in a conventional home, in a net zero home of the same size, you could probably size a 25 or 20,000 BTU system, and it would run your building just fine. The reduction in heat requirements also reduces your duct sizes, and that makes installation easier. It's easier to run a main duct that's 6 inches in diameter than to run an 8-inch by 30-inch duct through your building. So it makes life a lot easier there. Something else which I don't think I didn't put it in, but when your envelope is really tight and you're losing a lot less heat through your windows and your walls, you don't need to run your heat supplies in your rooms out to the exterior. So that lets you design a simpler system with less ductwork and provide your heat from the warm side of the room, and it's still going to keep the room comfortable. And that also, so that less duct work, less duct runs, and reduced duct sizes makes your system install easier and makes it easier to get a better building. And then you want to improve your duct sealing. So again, you want to put the heat in the places that it needs to go, put the cool air in the places it needs to go. So you've improved your leakage in your walls. You may as well improve your leakage in your heating and cooling system and make sure all the air goes to the places it's supposed to go to. All right, we're going to move on and talk about advanced water heating systems next. So water is expensive to heat, and there's no shortcut for it. To raise one liter of water 1 degree Celsius requires, I think, a kilojoule. I've been a long time since I was in school. Basically, there's no shortcut for it, and it's a high amount of energy. The words I remember are specific heat. Water has a very high specific heat, so to add energy to it takes a lot of heat energy. And if you recall on the pie charts that we saw, water really didn't change in size. It stayed at 15% to start with, and I think 20% or 18% in the net zero building. So there's not a whole heck of a lot we can do to reduce the. And I should point out, 20% of a smaller total energy total. We have flow restrictors and things that are required in a net zero building to reduce water consumption and specifically to reduce hot water consumption. So even though it looks like it's the same amount of energy, it's actually, that fit 20% of a much smaller total energy budget. So we are improving our ability to heat water as well. We have on-demand water heaters, and that's this guy here. You can see it's got an Energy Guide rating, and it vents to the outside, and cold water goes in, hot water comes out. It's on demand, so we don't have the cost of keeping it warm while it's stored. They're pretty efficient. We also have high efficiency natural gas, and this is a conventional tank, but we've got efficiencies now that are north of 90%, which is quite good. And these are condensing units as opposed to non-condensing units. Condensing is the more efficient it is, the more likely you are to have condensation when you have combustion of your gases. We also have heat pump water pumps. So this is a relatively new thing, at least in North America, and it looks like a regular electric hot water tank with a compressor sitting on top of it, and that compressor is used to run a refrigeration cycle, same as it does in a heat pump, except it's taking heat from your environment and putting into your water. And then we have drain water heat recovery. That's actually in the code, and it has been for a while. If anybody's been in the basement of a new build house, you're going to see somewhere in the corner where the stack comes down for your drain, this copper insert with this tube wrapped around it. And that's to take when you're showering and you're shedding hot water at the same time that you're demanding hot water. There's a heat exchange that happens here as the hot water leaves and the cold water comes in, so you get to recover some of that heat energy. And then we have hot water recirculation pumps, and this it's a way that you can use an on-demand hot water heater. One of the complaints about them is that you can turn on the hot water in your bathroom and you can wait sometimes up to a minute to get hot water at source. So the newer ones now come with a built-in recirculation pump and a small reservoir inside the heater. And you can set up a return loop that keeps hot water in the system so that when you turn it on, you get hot water instantly or virtually instantly, very, very quickly. There's no wait for the thing to start up. You've already got that little reservoir of water to supply. And that's an improvement in quality for your occupants, that you get hot water right away. And it means you waste less water as well. And now we're going to talk about efficient lights and appliances. And here it's with the goal of minimizing occupant energy use. So Energy Star appliances, there's no magic to this. Not all appliances have an Energy Star rating. You want to find, it's interesting, when you do your modeling for your net zero building certification, you have to provide the make and model of all the appliances that are going to be installed in the building, and they go into your energy calculations. So it's prudent to look at your annual energy consumption for your appliances when you're providing that to providing their make, model, and not serial number, but make and part number to your energy modeler, because he's going to go off and find that information and stick it into your energy model. The other one's LED lighting. That one's pretty obvious. And I mean, anything we build now or even renovate, we put LED lights in as a starting position. I don't know if you can buy a home now that has anything other than LED lights in it. And retrofitting them is fairly cost effective. And then auto shut off devices. So things that if you're not using them, they will shut down on their own for a while, like outdoor lights that are on a motion sensor, things like that. Yeah, there's not a ton you can do for occupant load, and these are the things that normally get factored into your energy modeling. So I'll talk about optimal site planning. There's limited uses for optimal site planning in urban locations. You're often, have a question?
Yeah, on the consumer load or the occupant load, what would you I understand Energy Star, I understand LED lighting, shut off and so on. Charging electric vehicles, that's going to be a huge occupant energy usage thing, and time of day is very important when we do that, and how that is metered and all the rest of it. So I'm just wondering if you have thoughts on that from an occupant energy usage perspective.
So some, yes. Time of day is not going to factor in because your modeling is done on an annual basis, and it's purely energy consumption. It's not cost of that energy consumption. So for net zero calculation purposes, it doesn't matter if it's gas, electricity, or what it is. It's purely kilowatts used or kilojoules consumed, and then kilojoules supplied by your whatever your passive energy system is. So it's purely it's an energy balance thing. It's not a time of day thing. When you're paying for it from your electric supplier, it's time of day that matters. So none of our buildings have car chargers built into them or designed into them, Dave. The one that we're trying to achieve net zero on doesn't have parking, so we didn't have to worry about it. And I can't honestly recall. I'm pretty sure if you tell them you're putting a car charger in, they're going to put a load in for that. How they calculate that load, I do not know.
Okay.
But it's going to affect the size of the solar array you'd need to achieve net zero for sure.
For sure, yeah. Okay, thank you.
Okay. So back to site planning. Again, in urban locations, your building envelope's pretty well defined on your lot based on the setbacks in your zoning. So there's not a whole ton of room to do work here. Although you can do things like plant trees. They may not affect it right away, but they'll grow and they'll provide the shading that you need for your glass areas during the summertime when they're up to a certain size. So building orientation and positioning, obviously, where you put your windows in your building as well. They're all going to affect primarily solar, but some other aspects as well. Again, if you can shield it from high winds, you're going to reduce your leakage in those sort of situations. Utilizing landscape and vegetation, again, incorporating trees can provide shade, also can provide protection from wind. Your renewable energy integration. So this is, excuse me, this is how do I optimize my building so that my solar array is oriented in the most effective way possible, so I can get the maximum energy creation from my exposure to sunlight. So in an urban setting, I'm skipping ahead a few slides. In an urban setting, the only viable means of passive energy creation is solar. If you're in a rural setting, excuse me, particularly if you're off grid, there's other means of providing that energy, that regenerated energy, or renewable energy, and so then your site planning can factor in things like where can I put a windmill, or am I close enough to a water course that I can put a mini hydro system in, something like that. But for urban purposes, best you're going to get is how do I orient my array, and can I put some trees there to help me with shading in the summer. Microclimate considerations, that again goes to setting up an environment where you can protect yourself from wind or shading, things like that. And this one's not necessarily net zero, although it is a little bit. It's stormwater management with your site planning, and that speaks to how do I keep moisture away from my building so that I don't have any water ingress or pressure differentials up against my foundation that'll cause leakage. So we want to plan our site so that we shed water and we don't have that challenge to our envelope. So that the last aspect of a net zero design is your on-site energy creation, your renewable energy. So the image I've shown here, this is what you're going to get in every urban residential application. It's putting as much solar oriented south as you can get. And if you can't orient it south, but you can orient it east and west, it's not as effective, but it's still better than not. And you're going to engage with well, your general contractor is going to engage with a solar panel supplier, and they're going to help you with your design to give you the most energy that you can get. So we have solar, obviously. Wind, you can put turbines up there. They're usually not allowed in urban locations. I know in Ottawa, you're not going to get permission to put a wind turbine anywhere on your lot. Geothermal, and that's it's pulling energy from the ground and using it in your building. And then finally, micro hydro. Again, you need some kind of a water course on your land that you can tap and put a hydro generator in. And of course, if it gets cold like it does here in Canada, you have to allow for the fact that things are going to freeze up in the winter. So that's again a pretty small sample size that can take advantage of that, but it's a legitimate way to create energy on your land. Excuse me. So that's a discussion about how you get to net zero, what you need to do to your building envelope, what you need to do to your systems, the requirement for ventilation as a result of the improvements in your building envelope, talking about user loads, and then talking about the renewable energy creation. So next question is, why would you build a net zero building? So let's start with the cost, and it's not a hidden cost; it's a direct cost. It can cost up to 20%. It can add up to 20% of the cost of a new building to deal with all the aspects of a net zero design, so that you arrive at a very high performing building. That said, the operating costs for a net zero building are dramatically reduced. Your utility costs can go to zero, and that has a big impact for a multi-unit building operator. It also eliminates your susceptibility to utility cost increases. If the hydro utility or the natural gas utility starts talking about increasing their cost or their base charge for something, it's not something that's going to concern you in the operation of your building. You're basically you're making yourself inflation proof from a utility perspective. This is an obvious one, not necessarily, but based on what I said earlier this evening, you're going to be compliant to future construction standards. So you're going to have a building that is going to, over time, remain relevant, hold its value, and yeah, you're not going to be stuck with the risk of an expensive future upgrade when the need for that net zero standard is mandated by the government. And if that will come to pass or not, there's a fair bit of discussion about that. But if it does come to pass, you're not susceptible to it if you've already built it into your net zero building. So why own a net zero building? Well, the first and obvious one is increased net operating income equals higher building value. If you're an investor or a developer, you know that the amount of money you collect in rent less the expenses you have to pay is your net operating income. And if you pay less expenses because your building is cheaper to operate, then your net income is higher and your building valuation gets higher. And it's not a trivial amount, right? A multi-unit residential building in Ottawa right now is operating at probably a 4.5% cap rate. So that's around 23 times. So if you can save yourself $10,000 on your utility costs in a year, that's going to come back to you as a $230,000 increase in your building value. So it's quite a big deal to increase your net operating income. You also have access to government financial assistance if you own a net zero building. The most specific example of that is the MLI Select program through CMHC. It's going to give you access to financing at very high loan to values, very low debt coverage, and at very low premium rates, and with great coverage. And you're to get that, you don't need to be a net zero building, but to get into that MLI Select program and not give up rent in the form of affordable units, you can do it this way and maintain market rents for all your units. You're going to attract eco-conscious tenants, and if you're doing it with investors, you're also going to attract eco-conscious investors. So your tenants it's an easy draw for your tenants. It's a much improved living environment when you have a net zero building. Finally, you're going to get enhanced brand reputation. You're going to be known for building good buildings. Tenants are going to want to live there, and you're going to give a good return to your investors because your building values are going to be higher. Your operating costs are going to be lower. It's a win-win all the way around. And finally, you're going to have improved air quality and consistent indoor temperature, and that's going to result in reduced tenant turnover. Once someone moves into a net zero building and they see how controlled the environment is. Fresh air is provided. They don't hear their neighbors because they don't have air leakage in the walls between the units. You're going to take, once someone lives in that environment, to move out of a net zero building and move back into a conventional building is going to be a big step backwards in their progression through improved living accommodations as they go through their life. So once someone comes into your building net zero, likelihood of them leaving to go to a non-net zero building is very low. So improve your tenant retention. And because these are all new built buildings, tenant retention is not a bad thing, because at the moment they're not rent controlled, so you can keep your rent at market even with the same tenants in there. Okay, so how do you build a net zero building? So you need a team. You're not going to do this on your own. We certainly don't. And the first member of your team, you need a net zero trained and certified builder. So net zero trained, you've been trained, you've done the course, you've got your certification for that. You have not yet built a net zero building. So when you've constructed your first net zero building, you transition from a trained builder to a certified builder. And this is the certification I got from the training I did last year. You also need an energy advisor. You'll recall from the definition very early in the presentation that you need attestation from an energy advisor, and there's a number of reports that have to get filed with Natural Resources Canada. And if you're using your energy improvements for your financing, that same energy advisor has to submit reports to CMHC as well. In our case, we use HomeSol Building Solutions. One of the gentlemen at HomeSol was actually the trainer for our net zero builder training, and they've been very good to work with. They'll also come in and help you if your other members of your team don't have that deep background in building science and net zero construction. HomeSol is happy to consult to make sure that you get a building that's properly done. Next up, you need an architect. We use Hamel Design and Planning, and they were not a net zero trained architect when we started to work with them, but they are now. I don't take credit for that. Stefan at HomeSol spent a lot of time with their architect, and he's now up to speed on what a net zero building looks like. And you're going to need engineers. And the engineers that we use for our net zero building are LRL Engineering. They're local. They're in the east end of the city, and they've been great to work with. Some of the engineering firms also will have the energy consultants and energy advisors. I'm not sure if LRL offers that, but they certainly have the expertise in their mechanical and electrical department to accommodate your net zero requirements in your building design. Okay. So review of net zero construction. We talked about what a net zero home and building is. We talked about energy use in net zero homes. We talked about how we achieve net zero, some of the risks that come with putting a net zero building together, what the costs and benefits are roughly. And we talked about how the developers use net zero. And then we talked to you guys about your net zero team. And I'm done.
So they want to turn off the recording.
I will do that as soon as I find my controls. And stop recording.